Welcome back. Today we're diving into the big topic of managing forest carbon. The goal here is to help landowners understand what they need to know when it comes to measuring carbon and making unit conversions. Forestry is all about those numbers. So we'll cover how to estimate carbon benefits over time in space too, so we can get to the point of understanding what is improved forest management and how can that increase carbon stocks. So let's get going. Today, we're going to be talking about both kinds of carbon, both forest carbon and carbon dioxide. Mainly, we're explaining the relationship between managing forest carbon and how to calculate those emissions that are reduced by keeping carbon dioxide locked up in that living biomass. So let's get started. First of all, it's important for landowners to understand that estimating carbon is a prediction. There are standard practices used to conduct a stand inventory, and those standard methods are usually done right before a commercial harvest to understand the value of the timber in the stand and the potential revenue that can come. Inventories can be done for multiple reasons, but in every case, there's the use of allometric equations. These allometric equations are based on the idea that some tree variables, like the circumference of a tree trunk, are proportionally related to other tree variables. And by measuring just a few key parts of the tree, we can understand the volume of wood per acre, which we can then use to calculate weight and carbon density per acre. There are a few key steps to estimating forest carbon. First, you need to determine the dry weight of the wood. There are a number of resources with tables of dry weights for different tree species. And next, identify how much of the dry weight is carbon. In most cases, it's about half the dry weight. On the right, you'll see a figure from a literature review summarizing studies on carbon content in different parts of the tree. The yellow and green bars show data on bark and branches. The purple bars are from studies that focused on the stems or the trunks. And the left axis shows the number of observations, and across the bottom is the percent carbon content. Most of this data clusters around 50% carbon, but carbon can range between 35 and 60% of that living biomass, depending on the species and which part of the tree you're looking at. As you can see, the stem or the trunk holds most of the carbon. Here's a great resource provided by Montana State University Extension Services, and it's a step-by-step guide on how to estimate the number of board feet in a tree. This is a great tool to use for a field demonstration. With it, you can walk your client through the process of measuring the amount of board foot or volume in a tree. Doing this can help connect the idea that carbon estimates are based on stand inventory practices. But we're not just interested in how many board feet are in a stand, since carbon is stored in more than just merchantable wood. And what's really important is that we want to estimate how much carbon is in the volume per acre. For that, we're going to focus more on the concept of basal area rather than board feet. And that's the concept your client really needs to grasp. Basal area is a quick way to estimate wood volume per acre by adding up the cross-sectional areas of all the trees in a plot. For example, you can have plots with different numbers of trees, but in plots with fewer trees, but they're larger, you can still end up with the same basal area as plots with a whole bunch of smaller trees. This figure shows how both tree size and number of trees per area affect total woody biomass. And that's where the carbon is. Whether it's in a branch or a stem, carbon counts the same. So managing based on basal area is key for understanding your carbon stocks. Of course, there are different types of forest inventories. We just talked about something called plot sampling, but there's also point sampling, which can be done through in the field or through remote sensing. In both cases, the goal is to estimate the total volume or average growth of biomass over time by measuring part of the landscape and scaling it up to the acre or to larger areas, and then going back and repeated measurements over time. While many forest inventories focus on volume to estimate carbon, there are other inventories that assess stand structure and species diversity. And that's important because the structure of a stand and its diversity relates to forest health and resilience, which affects how long that carbon is likely to stay stored in the forest. We are now using more advanced technology to support forest management. Things like drones, satellites, and airplanes equipped with lasers or LiDAR. These tools help map forest cover at both broad and fine scales, and each has different strengths in what it can measure. This is also how we get FIA data, the main forest inventory data used by the U.S. Forest Service. But no matter how advanced the technology, field verification is still essential to make sure that the data from above matches what's really on the ground. Project developers are increasingly using FIA data and remote sensing to identify where those carbon management opportunities are the highest on family forest lands. From there, they design and launch projects based on those insights, and remote sensing is the key to scaling up efforts and making carbon management more accessible for private landowners. Another key technology for helping scale up forest management is machine learning or artificial intelligence. These systems use data to train algorithms that improve over time, similar to how humans learn, making them better at analyzing and predicting forest conditions. A review by Sharma found some machine learning models reached 93% accuracy in classifying forest area and 80% accuracy in detecting risks like wildfires, pests, and disease. That's impressive. However, estimating things like timber quality and carbon storage is more challenging, and the accuracy can vary. Still, forestry is heavily investing in AI because it's efficient, it can cut costs, and can bring together useful data like climate variables for forecasting. It's also a promising tool for scaling forest management across large landscapes so that the same number of people can cover a lot more forested area. There are a lot of unit conversions involved when estimating emissions reductions, and it can be a little overwhelming. Luckily, many forest inventory tools now have it built in. When you enter stand inventory data, the programs will handle those calculations. Still, it helps to understand what's happening behind the scenes. You're often moving between English and metric units, then you convert wood volume into weight, which depend on species. So if you remember, pine tends to be less dense and hold more water than hardwoods. You also have to count for wet weight versus dry weight. Finally, once you estimate forest carbon, you convert that into carbon dioxide equivalents, but not because it's being released, but to understand the potential emissions if that carbon were to be released through decomposition. And that's what helps us quantify avoided emissions. So let's start with basic chemistry. Carbon has an atomic weight of 12, and oxygen is about 16, so when carbon bonds with two oxygen atoms to form carbon dioxide, the total atomic weight is 44. This means carbon dioxide is 3.6 times heavier than a carbon alone. So for every ton of carbon stored in a forest, it's equivalent to 3.6 tons of carbon dioxide emissions if it were released. This is a key conversion, giving us a clearer picture of the climate benefits of managing carbon stocks in the forest. Here's another table from the guidebook showing common forestry conversions that help us estimate emissions. It starts with things like a cord of green stacked pine, with or without bark, and breaks down the weight in pounds for both pine and mixed hardwoods. From there, you can see that you can convert volume from cubic feet and meters into weight, depending on the species. Next, you calculate the dry weight, which also varies by species. On the far right, you'll see that the metric tons of carbon, and next to that, metric tons of carbon dioxide emissions, is somewhat bigger, and that's due to the 3.6 conversion factor we talked about earlier. Here's one key point. These calculations only apply to additional growth, not the total biomass on the landscape. So we're not counting everything that's already in the stand. We're only interested in the extra carbon stored because the forest has managed to grow beyond what it normally would have under a business as usual plan. It is that extra growth that represents the avoided emissions. Let's take a look at this example of how carbon density changes over time. This is from the Forest Service lookup tables discussed in Module 6. And you can see that across the bottom is the age of the stand, which is increasing over time. And then the carbon per acre is on the left, and that is also increasing. Obviously, the total amount of carbon increases over time, but most of that is in that gray line, the above ground living biomass. And that's a lot more compared to what's below ground, what's in the roots, which accumulates carbon more slowly. So let's consider this baseline scenario in this slash pine. Let's say the stand would normally be harvested at age 25. At that point, it holds about 65,000 pounds of carbon. That's our baseline, or business as usual. Now, if we delay harvest by 5 years and the stand is projected to store an additional 7,000 pounds of carbon, that's the extra carbon that's considered additional. It is the gain from delaying harvest. Carbon accumulated before age 25 doesn't count towards emissions reductions because it would have happened anyway. So when we're talking about climate benefits, we're only looking at the extra carbon added above the baseline. But that's not the whole story. You also have to track carbon stocks over time. It's not just about measuring additional carbon at harvest, but comparing it to that baseline across time of the project. In this example, the gray line shows a regular harvest rotation, the business as usual scenario. The green line shows an improved forest management scenario where harvests are delayed or reduced. Because of that, more carbon stays on the landscape over time. That sustained difference in carbon stocks is what counts as additional carbon storage, and again, ties back to basal area because it reflects the volume per acre that's being added. You might be wondering, what happens to those carbon benefits after the harvest? Do we lose them? That's where we have to zoom out even more and think like a project developer, looking at carbon storage at the landscape level and not the individual property level. In this figure, the bars show properties enrolling in a carbon project every 10 years. Each one manages its stand to delay harvest and increase carbon storage. Even if one property drops out after a decade, another steps in. So over time, carbon stocks remain elevated in the region, but the carbon is just stored on different properties. It's like a football being handed off from property to property. This approach keeps overall carbon stocks higher than it would have been in the area. And it also means that developers need to carefully track and account for these shifts to ensure that overall benefit is real and verifiable. This video introduced concepts about how forest stocks are measured and how delayed harvests can be used to increase basal area over time. Carbon estimates are predictions of both current states and future states, and also the future alternative state, what would have been under that business as usual and what is occurring under a delay harvest. What often determines the value of the carbon credit is the potential error in these estimates. It's the amount of confidence in how carbon is managed and quantified that really determines its value to buyers. We have some reflection questions for you all to consider. First, consider how important is it to your client that the carbon benefits be measured accurately? In some cases, you can still provide climate benefits even though you don't know exactly how much carbon is being stored. But if you're going to sell the carbon, it has to be measured very accurately. Also consider, what is the structure of your client's forest? What is that species composition? Because this is going to impact the way that you measure and manage carbon. Thank you for joining us. The next video, we're going to discuss how landowner values fit into the decision-making process and what is this improved forest management. If you're watching this video on YouTube, please check out our free online educator course. If you're taking this course, here are a few reminders. Make sure to complete the comprehension check and the survey at the end of the module, and leave us questions in the classroom forum, and we'll get back to you. See you next video.